Welcome back. Today we're going to do an optimization problem with the island and the shoreline and a restaurant. You've probably seen some version of this problem at some point in your AP Calc or Calculus 1 class, but if you haven't, here it is. An island is 3 miles north of a straight shoreline. Okay, cool. Let's write that down right away. Here I have my island, and then here I have my straight shoreline like that. And we know that this distance here from the island directly to the shoreline is 3 miles. Okay, very good. A restaurant is 10 miles east of the closest point on the shore. Okay, very cool. So that means that here, let's have our restaurant be right here. And I'll label it as R for restaurant, and I'll label this as I for island. And this is 10 miles this way, like that. Okay, very good. Then it says if a swimmer swims 2 miles per hour and walks 4 miles per hour, find the optimal landing point to minimize time and find the minimum time. Okay. And in some versions of the question, you might be just asked to find one or the other, but I'll be going over how do we find both today. The nice thing is once we have found the point at which we could minimize the time, finding the minimum time itself is not that much extra work, which is the good thing. Okay, very good. So first, I'm going to talk about what path we're going to take. So essentially what's going to happen is we're going to start at the island. We're going to go this way, to some amount here. We're not sure exactly where. That's what we're trying to figure out. And then we're going to walk the rest of the way. So of course, the shortest path in terms of, not in terms of time, but in terms of distance would just be to go directly there. However, we don't actually know that that is the actual shortest time in terms of time-wise, because it says the swimmer only swims at 2 miles per hour, but they walk twice as fast. They walk at 4 miles per hour. So it actually may be advantageous for this person to just kind of swim on an angle, swim part of the way, and then walk the rest of the way, because as soon as they get to the shore, their walking speed is twice as fast as their swimming speed, which makes sense, right? Most people can walk or run faster than they can swim. Okay, so next what I'm going to do is I'm going to label these. I'm going to label this unknown right here as x. And then this would be 10 minus x, right? Because we know this full length is 10. So if I'm labeling just this part x, then this part must be 10 minus x. That means that the swimming distance must be x squared plus 9, right? Because if we assume this is a right angle, since it's due north and goes to a straight shoreline, that means we'd be able to use Pythagoras' theorem of 3 squared plus x squared to be able to get the hypotenuse there. Oh, and I should square root that. My apologies. The square root of x squared plus 9 would be our swimming distance. And our walking distance would be 10 minus x. So I'm actually going to write that down, that our swimming distance is the square root of x squared plus 9, and then our walking distance would be 10 minus x, like that. So what would the total time be? Because ultimately we want to find the x value here, right? We want to find the optimal landing point that will minimize the time. We need to know how far from the restaurant should we land in order to minimize the time. And then we also need to know what is that minimum time. So let's write the equation for the time. So the time is going to be the swim distance divided by 2, right? Because it's 2 miles per hour. And then we're going to add that to the walking distance over the walking speed, which is 4 miles per hour. And so there we go. All right, so then our next step is going to be to take the derivative of this. So let's go ahead and do that. Let's take our derivative. So before I take my derivative, I'm actually going to get this into a more optimal kind of format, I would say, in order to take my derivative. And what I mean by that is I'm actually just going to switch the square root sign to power of 1/2, just because I think that'll make it easier to use the chain rule for this first part in order to actually find that derivative. So let's find that derivative. Okay, so the derivative, a reminder that we are going to take that power and we're going to multiply it to the full thing. So we're going to get 1 half times x squared plus 9 over 2. So everything else exactly the same as it is. And then we're going to have it be to the power of negative 1 half because we subtract 1. And then what do we multiply by? We multiply by the derivative of x squared plus 9. So derivative of x squared plus 9 would just be 2x based on the constant rule and the power rule. So times 2x. Now I'm going to clean this up in a little bit because obviously that doesn't look so great, but that is okay. Then what about this next part? Recall that 10 minus x over 4 is the same as 10 over 4 minus x over 4. And the derivative of a constant like 10 over 4 would just be 0. The derivative of negative x over 4, or in other words, negative 1/4 times x would just be negative 1/4. So I'm going to subtract 1/4. And now we found our derivative. Now I will clean this up a little bit. I'm going to note that this 2 can cancel out with this 2. Also, the negative 1 half can be moved to the bottom. So we can rewrite this as, let's see, 1 over 2 times the square root of x squared plus 9 minus 1 over 4, like that. Okay, very good. So now that we've rewritten that, the next step we need to do is we need to set the time, or not the time, the derivative of the time to be 0. Now, why are we doing that? We're doing that because in general, whenever we're doing an optimization question, in order to find the minimum or maximum, one key element is we must take the derivative of the whatever it is we're trying to optimize and then set it to 0. Because reminder that when our derivative is 0, that is the point where that would indicate a minimum or a maximum, or a different optimal value, but in this case, a minimum or a maximum, specifically a minimum here. Okay, all right, so now let's set t prime of x equal to 0 to get that 0 is equal to x over 2 root x squared plus 9 minus 1/4. So therefore, 1/4 is equal to x over 2 root x squared plus 9. So therefore, 2 times the square root of x squared plus 9 is equal to 4x. Then if we continue up here, we're going to get that the square root of x squared plus 9 is equal to 2x. Then if we square both sides, we get that x squared plus 9 is equal to 4x squared. Therefore, 3x squared is equal to 9. Therefore, x squared is equal to 3, and x is equal to the square root of 3. Okay, very good. So now we figured out that x is equal to the square root of 3. So this would be root 3. This would be 10 minus root 3. And this here would be root 3 squared plus 9 and then square root of that, which would be root 12. However, that's besides the point. The point now that we figured out that the optimal landing distance is 10 minus root 3 miles from the restaurant, we need to know what is the minimum time. Okay, so to find the minimum time, I'm just going to plug that value of root 3 back into my time equation. So here I've just copied my time equation onto another page because we were running out of room. So this is going to be t of root 3 is equal to root 3 squared plus 9 to the power of a half over 2 plus 10 minus root 3 over 4. So root 3 squared is just 3. So over here we're going to get root 12 over 2 plus 10 minus root 3 over 4. And then that's not really something that's going to simplify super nicely, which is okay. So I'm just going to use a calculator to figure it out. For this part, it's approximately 1.732. Then for this part, we're going to get 10 minus square root 3 divided by 4 is about 2.067. So that overall would approximately be equal to 3.799. And what were the dimensions again? They were hours. So that is about how many hours the plan will take. Now, as always, if you do have any questions, feel free to leave those in the comment section, and we'll see you for the next one.